Okay, so we'll start our second session of day one with Xiaoxiang giving a talk on Llarull type rigidity for compact domains in a warped product.
Sorry, there's a broadcast.
What was that? Sorry, sir.
Okay.
Yeah.
Okay, there was a broadcast in my room, so.
I gotcha. Yes.
So today I'm going to talk about Llarull type rigidity for compact domains in a work product. So let's see the most classical results on scalar curvature rigidity. So everyone knows this Gauss-Bonnet theorem, which says that if you have a orientable surface with a metric gamma, and then the Euler characteristic is the total integral of Gaussian curvature and total geodesic curvature on the boundary, and then if your boundary is non-smooth, and then there is a boundary term, which is the summation of the exterior turning angles of these boundaries. So from here, you actually can get basically all the two-dimensional rigidity results, as we already see from talks from the first half of today. We have the Llarull conjecture. So other than the Llarull conjecture, other higher dimensional generalization of this rigidity, at least here, regarding to the rigidity of spheres, disks, and polyhedra, are basically conjectured by Gromov with different kind of motivations, I think. So if you have any arbitrary metric on some model manifold, and then you have curvature constraints, say for a geodesic curvature or angle comparison, things like that, then you can have some rigidity of this model metric. So the two-dimensional rigidity, at least here, basically you just plug in these curvature constraints and you can get immediately rigidity from the equality sign, very elementary analysis. So as we know, scalar curvature is the very weak curvature because it's the trace of the Ricci. And locally, you can control, locally you have a volume expansion with respect to some geodesic normal coordinate. But globally, you don't have such things. There is no diameter control. There is no volume control. For example, you can just think about the long tubes and then cut it off and then attach it with spherical caps, half spherical caps, and then you get a control example if you assume these geometric controls. So another thing I want to mention is that, which is a higher dimensional generalization of this polygon rigidity by Gromov in 2014, which his motivation is trying to define the weak notion of scalar curvature lower bound. So today I'm going to talk about basically these two type of things if you assume some additional conditions. Yeah. So first of all, I would also like to review this Llarull conjecture, which says that if you have a metric on the torus, and then if you have a scalar curvature is bounded by 0, then this metric G must be flat. So this is kind of like the first scalar curvature rigidity maybe in higher dimensions. So there are many proofs nowadays. The first proof is by Shen and Yao using minimal surface under dimension 7 because of singularities in error minimizing surfaces. And then there's Gromov-Lawson in 1983 using the spinors. And then recently in 2022, Stern found a very elegant proof using harmonic functions or harmonic maps. So let's take a look at this Shen and Yao's proof using minimal surface. So you have a manifold M, and then consider a hypersurface, and then you consider the area of a sigma. And the first variation, as is well known, gives you the mean curvature of this hypersurface. So the minimal surface is just a critical point of this area functional, or you can define like the mean curvature is identically 0. So in the case of a torus, you can find the error minimizing hypersurface in the n-1 homology class. And here I'll give the example of dimension 3. So it's considered a T3 or 3-dimensional torus. And so after you find the minimal surface, which is error minimizing, obviously the stable, and then you have the stability, which is in terms of analysis, is just saying that the second variation of area is non-negative. And so what Shen and Yao find, their trick is rewrite this second variation of area. There is a Ricci term. They rewrite this Ricci term. So this is almost very well known trick in scalar curvature geometry. And then because we already know that mean curvature is 0, and then the second fundamental form of this hypersurface is non-negative. So basically, you ended up with an equality which only have 3 terms, which is the scalar curvature of the manifold, of the 3 manifold, and then the scalar curvature of your hypersurface or your minimal surface. And then because you're in dimension 2, you take your test function.
The scalar curvature of the manifold.
Yeah, R here is the scalar curvature of the manifold, and R sigma is the Gaussian curvature of the hypersurface. And sorry, I missed zeta here, zeta squared here. So and then you plug in for zeta equals identically to 1, and then you don't have the gradient zeta squared term, and then you can apply this Gauss-Bonnet theorem. And with the rigidity analysis nowadays is pretty much standard using this trick from Fisher Corporation and Bray Brando Neves result. So yeah. And so as my title of the talk suggests that we're going to be concerned with raw product, so I should introduce some terminology. So raw product is just a metric of the form dt squared plus phi t squared plus some metric of there shouldn't be j's and so on with some manifold over some of another manifold is called raw product. So phi t is called a warping function, and then you have a factor or warping factor. So the second rigidity result I would like to talk about is the rigidity of the hyperbolic class cusp, which is you consider the n-1 torus times an interval. If you have now the scalar curvature bound, the lower scalar curvature bound now is minus m times n-1. And then you have, if you have, because now the manifold has a product structure, it has 2 boundaries. So you also need to take the mean curvature into consideration. And the curvature bound for that is the top has minus n-1 as a mean curvature bound, and the bottom has n-1. And then this metric G must be hyperbolic in the sense that it must be isometric to some warp product over this n-1 torus. Or you can write a slightly different way in a conformal form. We're going to talk about this conformal form later. So this is a proof by Xiaoxiang Chai and Galloway in 2008. I think before them, there is Witten and Yao. There's an archive paper on this. I didn't check very carefully, but I think they have also mentioned this maybe. Okay, so yeah, so the basically the proof is about the same. You find the surface of mean curvature n-1, and then the stability of this is actually formally is the same with the stability of the minimal surface. And then there's a slightly bit difference on the estimates of the second fundamental form, which you estimated by because our mean curvature now is n-1. So the second fundamental form must have that, at least that magnitude, right? So it is given by 1 over n-1 h squared, plus the traceless part of the second fundamental form. So after that, you use the Shen-Yao's rewrite again, and plus this elementary estimate, you will get this estimate on the Ricci term and the second fundamental form term, and basically that will give you the rigidity. So as for the boundary, because you have a boundary, and then these boundaries will act as barriers for the existence of mean curvature surfaces. And next I would like to talk about this bandwidth estimate, which is also warped product over the n-1 dimensional torus. So the first one is given by Gromov, which says that if you have a segment times the n-1 torus, and then if you have a metric G with positive scalar curvature bound, which is the scalar curvature of the m-dimensional sphere, and then the bandwidth of m must be less than 2 pi of n. Less than 2 pi of n. The bandwidth here is just defined to be the distance of two boundary components. So this theorem says that if you have a positive scalar curvature bound, then this bandwidth, at least in one dimension, it cannot be too big, which is the dimension of this segment, actually. And so Gromov also introduced this orthogonal band. It just says that if you have a continuous map, which is non-zero degree to this torical band, and then he called this band orthogonal band. So basically, this orthogonal band is just says that the manifold with two boundaries must have the topology as complicated as the torical band, as this torus times some interval. So as in the statement of theorem, there is some rigidity statement, which was actually not proven yet. This bandwidth estimate is realized by this metric, which we can see actually is a warp product, and the warping factor has something related to the cosine. And I think this is too small. I didn't cover this. there is also some rigidity bands for negative curvature band and zero curvature band. Actually, these bands are not compact, so you would need some boundary mean curvature comparison on your band to get some bandwidth estimate, but that is a minor issue. So there are many developments of this bandwidth estimate. So Sekini and Ziedler in 2024, they used the spinor method to generalize to, I think, mostly in the spinor area, like a lot of bands with a different kind of topological conditions, which I'm not an expert in. And then there's Rod in 2023, and he gives the mu-bubble proof of this form of bandwidth estimate, and he also generalizes in some cases. And then there's a very interesting proof by space-time harmonic function by this Hirsch, Kadoras, Curie, and Zhang in 2022. Very interesting proof. So the idea is use this stable mu bubble. So what is a mu bubble? Is just a prescribed. So because behind this bandwidth estimate, you have a model metric or rigid band in mind. So this will give you some function, which is the mean curvature of the level set with respect to this wall product metric, so the rigid band metric. And then you try to find a surface of mean curvature given exactly by this function h bar. What you do is trying to minimize this kind of functional, of course, and then this will give you a surface which is minimizing and with prescribed mean curvature h bar. And the stability inequality now, or in other way, the second variation of this energy functional would have an extra term, which is the normal derivative of the function h bar, right? But actually here, h bar is kind of not explicitly defined yet. We just have some vague idea of that it is given by the level set mean curvature. So it is not defined yet. What you do is you pick a Lipschitz function such that the Lipschitz constant is 1, and then you will have some estimate of this function h bar, which is that you compose this function h bar with phi, and then you would have some estimate over this h bar composed with phi, and then you plug it into the stability inequality. And so this will give you exactly the scalar curvature of your rigid band metric or background metric. And from here, you can do the analysis like before. So Gromov also asked this question. So he tried to generalize or define even weaker concept of scalar curvature lower bound. So what he come up with is that he asked what is the positivity of the operator minus Laplacian plus gamma times the scalar curvature has on the effects of topology or geometry. So that gives naturally to the notion of a spectral curvature lower bound. So this notion is actually also popularized, is very popular since this the solution of a spherical conjecture and the stable Bernstein conjecture by Chodosh Lee and Minter and Stryker, and recently by Mazzetti in dimension 3. There are also some interesting results by Caron and Rose, and recently by Antonelli Xu. So here I listed this result by Antonelli Xu, which says that if a manifold M is complete, and if you have a spectral Ricci curvature bound on the Ricci, which is given like minus gamma Laplacian u plus u times the Ricci. Here the Ricci is defined to be the smallest eigenvalue of the Ricci tensor. And if you have a bound on this operator, and then you would infer that its diameter is controlled by a constant related to u and lambda and gamma, and also the dimension. So that means, so their proof is based on the unequally warped product. Unequally warped mu bubble. So I think one of the implication of their paper is that you can see this Bonnet-Myers theorem can also be understood as a bandwidth estimate. And actually, this was previously also mentioned by these 4 people, Hirsch, Kazuras, Curie, and Zhang. They used a different method. Actually, I think this Antonelli Xu theorem can be potentially, possibly weakened in some places. Maybe the completeness can be removed as well. But that is also a technical issue, though. So, so what is a warped mu bubble? So the most general form is that if you take the function u in the previous slide and then add this weight to the area and to the other part of the functional, and then you will get this unequally weighted warped mu bubble. So the first variation, and you can calculate that. Okay, so we also did this spectral bandwidth estimate idea, and then we proved some theorem to generalize something like we add some topological conditions which we require this manifold to be the n-1 torus times some segment or interval. And then we added some spectral scalar curvature bound. And with some special conditions on the constant gamma and big lambda, then we have some width estimate depending on gamma, n, and lambda. So of course we find the rigid metric rigid band for this spectral bandwidth estimate, but unfortunately we cannot prove the rigidity. We proved some weak version of this rigidity statement, but actually this bandwidth rigidity is not new. It was previously known by these 4 people. I mentioned at least 3 times now. They used the spinor and space-time harmonic function and mu bubble with gamma equals to 1. The interesting thing is that we restrict it to dimension 3 and we replace it to the scalar curvature to Ricci curvature. We can prove a spectral analog of bandwidth estimate of Jintian Zhu, so which is the case of gamma equal to 0. So in some sense, this I would think this is a proper generalization of this bandwidth estimate, which also comes with some rigid band. And again, the the drawback is that we cannot prove the rigidity. Okay, so next I would like to talk about the Llarull theorem, which is related to spherical wall product. So Llarull theorem is actually also conjectured by Gromov and then first proved by Llarull, which says that if you have a metric on the n-dimensional sphere, if you have a metric comparison, which is g greater than the standard metric, then either your scalar curvature had some point which is less than the background metric, which is or the g is identically equal to the standard metric. There are many proofs and generalization of this theorem. So in dimension 3, there is a Gromov and Hu Liushi and later Xueyuan Wan and Xian Zhu make some very clear observation, and then they generalize this proof to dimension 4. Of course, the higher dimension than 4, and using mu bubble is still open, of course. And then there is the 4 people using space-time harmonic function, and also some spinor methods as well. And so the motivation behind this is that Gromov trying to measure the size of the manifold in terms of spheres. So he considers the supermon of some radii if a manifold X had some map which is 1 Lipschitz and non-zero degree to the sphere with radius r, and then they call this quantity called the hypospherical radius. And then you can reformulate your Llarull has a reformulation of this theorem, which is in terms of these maps, which is has a Lipschitz constant less than 1, and then with scalar curvature comparison. And then he concluded that this F must be isometry. So this smooth, it turns out, can also be replaced by Lipschitz. And actually, this is done by Zucchini, Hankey, and Schick in 2002. They replaced the smoothness by Lipschitz. So after you know this reformulation in terms of a map F, and then you can reformulate your Llarull theorem presented in the slightly earlier, and then you can express your Llarull theorem entirely in terms of this hyperspherical radius. So the philosophy behind this is that if you have a big curvature, then the size of a manifold, which is expressed in terms of this hyperspherical radius, must be small, as you can see from this inequality already. So we are interested in this warp product, right? So here's this exact statement. You would have some metric comparison and then scalar comparison, because now we are in the warp product and you have 2 boundaries. You need to put mean curvature comparisons on the 2 boundaries. And then you would have rigidity. And the proofs is by an observation is that as I mentioned, I think multiple times, is that you observe that this standard 3-sphere is actually foliated by 2 spheres with a certain mean curvature on the level set, right? And you repeated the proofs I given earlier. And we are interested in the Llarull theorem with boundary, which is more general than the manifold with the 2 boundaries, one top, one enforced. So we would consider like a disk in the 2-dimensional, in the 3-dimensional sphere or higher dimensional sphere. And this goes back to my picture earlier, which is 2-dimensional rigidity. We are concerned about now because we are considering the manifold with boundary inside 3-sphere. So we are at the same time considering the second and the third case. And so this is not yet. We are considered about these 2 cases. And so let me review this Euclidean first. So we're moving his 4 lectures on scalar curvature. He have this conjecture or question or theorem. He says that if you remove the north pole and the south pole of the unit ball, and if there is a map from some manifold to the unit ball, which is 1 Lipschitz and a non-zero degree, and then there must be a point on your manifold which must have a mean curvature less than n-1. You rewrite this Gromov question slightly, or more in a more stronger way, maybe, which is that if you have a disk and then you put a metric on the unit ball, which have induced metric on the boundary, sigma is greater than sigma bar. And then on the boundary, you have a mean curvature comparison, which is h greater than n-1. And then on the interior, you have scalar curvature bound, which is greater than 0. And then you would conclude that, oh, sorry, I didn't write the conclusion. So then you will conclude that this comparison, this metric G is actually flat. Here, actually, this statement is stronger, is weaker than what Gromov proposed, because he doesn't, here we also require the comparison on the North Pole and South Pole. I would conjecture similarly as to Llarull's theorem that if you remove many points, it's also possible to have such a theorem. So there are many people working on this previously. So Gaoming Wang and Zhizhang Xie, they used spinor methods. And then me and Gaoming Wang, which is in Tsinghua University, we generalized this to rotationally symmetric sets in dimension 3, only in dimension 3. And then last year, this Dongyun Ko and Xuan Yao, they generalized to convex sets and a different type of listing called the listing type comparison, which actually includes the comparison of the metric. And then there's this work by Gaoming Wang and Zhichao Wang and Zhu Bo, which they proved that actually this theorem holds for arbitrary dimensions. What they use the method is non-spin, so this is a very good work. So Gromov also asked the hyperbolic case, which is when you replace the curvature bound by a -1, what kind of things you would get. So this is exactly the snapshot of this for lecture notes. Basically, the comparisons are all the same. You would have some comparison in the interior, on the boundary of the mean curvature and metric. So Gromov constructed this theorem. In the previous talk, actually, Pascal Mondal also talked about this theorem. His theorem is slightly weaker than this one. Yeah, but I'll mention this later. So again, we reformulated in a easier fashion. So we have geodesic ball B of radius r, and then consider another metric which have these comparisons like scalar curvature, mean curvature, and then the induced metric on the boundary. And then the conclusion is that this metric must be hyperbolic, and actually the induced metric on the boundary must be the same. So the natural question is that what kind of domains have this kind of rigidity in work product in general? So this is asked by Gromov in some way. So he asked, what is an adequate version of the log convexity condition on these measures? Actually, the measures is related to the mu bubbles. And then he asked find all the interesting sharp capillary extremity rigidity inequality. Yeah, so this is Gromov's question. So we give an answer to this question, which is in terms of sphere, we write this sphere in a work product form, and then we introduce a reparametrization, which turns the standard random metric into a conformal form, which is conformal to a direct product metric, ds squared plus the lower dimensional sphere. And what you can do is having a Llarull type theorem for the domain which is convex with respect to the metric ds squared plus the m-dimensional sphere. So the comparisons are exactly the same. You would have metric, scalar curvature, and the mean curvature on the boundary. These comparisons are all the same. And then you have the metric is actually identically equal to G bar. So so you can, so here this theorem is quite specialized in the sense that we only consider about the sphere. So actually you can also consider replace the warping function sine t by any positive function satisfying this log concavity, which appeared in Gromov's question. So, and also the n-dimensional sphere, you can replace it with any metric of a positive Gaussian curvature or flat metric even. And also when this omega is rotationally symmetric, and in the sense that is in the case of sphere, it is symmetric. Is symmetric with respect to one geodesic from North Pole to the South Pole. And then in this case, the convexity with respect to the direct product metric is actually equivalent to the angle forming by the level set and the boundary of omega is decreasing. So this gives an answer to Gromov's questions about finding adequate versions of this log-concavity condition of the warping factors. Okay, so what we do is that we first consider some good cases, which that actually have some corners. So these red lines are again formed by the level sets, and your region omega is this irregular shaped black version, black lines, and then you would have some angles forming by your level set and this part of the boundaries, right? And then you try to, because you have this part, you would have good barriers. But you need some angles conditions there, and this will give you some the barriers of the surface you want to find. So the explicit way to do that is by finding some set E. I took out the region here. Finding some set E, which is a critical point of this energy functional, which is the area of the reduced boundary in the interior minus this integral, and on the boundary this cosine gamma bar. So this would give you the minimizer of this energy functional will give you a surface which is of prescribed mean curvature h bar, and sigma would have a contact angle which is given by the gamma bar. So the rigidity then follows by some analysis of the second variation. So this approach was previously by 3 groups of people, as I have mentioned actually. I think Xueyuan Yao is going to talk about later, so I will not go into detail of this proof. So I would like to mention some interesting cases, which is the cases with conical points. So because we have barriers, right? But you have a top barrier and the lower barrier. The top barrier and the lower barrier are both a surface with boundary. So there is a case that it possibly collapsed to some point. They would collapse to some point on the radially geodesic. So in this case, we can also have a proof. And currently, we can only prove that this theorem is true in the rotationally symmetric case, meaning that this region, this triangular region or cone region is rotationally symmetric. So in rotationally symmetric just give you some conditions on the cone that is easier to analysis. So in general, we don't know how to do this. This is actually, I think, very interesting, but I cannot do it, at least. So Another possible case is that this cone point actually can go to the North Pole, all right? Can actually go to the North Pole. For this case, no matter what the shape is, we can actually prove that we can prove this theorem no matter what kind of shape of this cone region is. So it doesn't require the symmetry of this region. So in this case, I would just like to describe basically what is the proof looks like. So we consider a tangent cone at this North Pole. And in general, you can write this metric near this North Pole in a very canonical way, which is this dr squared plus r squared plus g section plus some lower order terms. So you get some radial parameter. And if you have if you have different tangent cones, and you have a metric comparison, right? And you take the level set of this radial parameter because you have two metrics which are both is of a cone metric times some lower order terms. You take the level set of these radial parameters, and then you would get some comparison between this of these radial parameters given by the metric comparison if they are non-isometric tangent cone. And then the sigma t would approximately have a metric 2 over t. And on the other hand, the sigma prime of S would have approximate 2 over S. And if you take the sigma prime S to be the barrier, this will give you exactly the mean comparison you like, plus some lower order terms because the metric is had some lower order terms. And then you do some perturbation, and this would give you an strict comparison of the mean curvatures, and this will give you the barrier, which reduces to the case with barriers. And then what about the angle? It turns out when you go to the North Pole, if you take level sets and every radial direction, because you are in the cone metric case, every radial direction will be orthogonal or approximately or near orthogonal to your level set of S. And this is very good. And you can also like have a perturbation on the boundary, and then this will give you a strict comparison. So this is the idea behind this the case of the cone type proof. So of course there are some spinor proof of these results. So for the hyperbolic case, we have this theorem, which says that if you have a compact, strictly convex smooth domain in the upper half plane, and then you have your hyperbolic metric B, which is a conformal form, delta over x1 squared. And then if you have another metric which have these comparisons, and then you would have your metric G can actually have no choice but to be hyperbolic. And also the induced metrics on the boundaries agree. So this is the previous result I talked about, that you can replace anything, the warping factor, you can replace it with a flat metric. Here we are exactly doing that, replace it with a hyperbolic metric. So there are some previous results by Gaoming Wang and Zhidang Xie, which they consider the radial convex sets, which is have some drawback, which this region must always have a base or top. And then I learned today that Monda actually used a different approach. He proved geodesic ball case. So as you can see, you can just take a ball on upper half plane, which is exactly give you the hyperbolic geodesic ball case, which is actually also conjectured by Gromov. So how to prove this by spinor methods? So our contribution is that again, we write this metric in a conformal form, and we have a direct product metric. And we take the spinor model with respect to the metric G. And then instead of consider the metric, the spinor bundle with respect to G0, we consider the spinor bundle with respect to G bar. And we twisted this spinor bundle with respect to G by the spinor bundle by direct product metric. And then we introduce this connection, which looks kind of complicated. So which basically means that we so this will give you the usual derivatives on the twisted spinor bundle. We add some perturbation term. So this does not change anything on the index. So starting from here, we can prove the theorem. So I would like to compare this spinor connection, because as I mentioned, previous results use a different spinor bundle, which they use the spinor bundle with respect to G0. And they consider this fiberwise spinor bundle. So first they have some connection on the spinor bundle with respect to G0, and then they define this connection by adding this term. Sorry, there's no tilde here. They add this perturbation to here, and then they proceed by using some Penrose operators. I would like to comment that this connection is actually could be possibly equivalent to our spinor connection, but we didn't do the calculations. I'm sorry. So we didn't do the calculations for this because it seems quite involved. So yeah, so we could also use the same technique, prove the hyperbolic dihedral rigidity, which you take a convex polytope in the upper half plane, and then you have comparisons and the mean curvature and angles. Here we use the Brendel's smoothing method, and using the same spinor connection, we can prove this result. So there are many previous results using different methods. It turns out that our connection can also be applied to polyhedral initial data sets. How much time I have? Okay, I think I have 5 minutes or something.
Yeah,
I will be very
minutes.
brief. Oh, 5 minutes. I will be very brief on this. So the initial data set just comes extra with a symmetric two tensor, and we generalize this scalar curvature bound and boundary mean curvature to this dominant energy conditions called. So we have this these comparisons, and then we get some structure of this polyhedral initial data sets. So as before, we consider the twisted bundle with respect to this flat metric. So we just change the usual connection on the twisted spinor bundle plus some extra terms. There was a previous result by Brando and Cho, which they don't have. What they don't have is this term. They replace it with 1. Yeah, so that's what I wanted to say, I think. Thank you.
Thank you. Thank you for the talk. Are there any questions? Or does anyone have any questions? Maybe a quick one or two before we have to move on. Okay, if not, maybe I can ask a quick one. So at the beginning, you said, right, Gromov has this over torical rigidity theorems for these bands. For your results, are there ways to phrase something where you could do over these bands and get rigidity?
There is some way, which is that because naturally you have work product, right, on the historical bands, and then this will give you a function, which is the coordinate of this segment, right? You put some conditions on the gradient of this coordinate, which is the gradient, the norm of the gradient is less than 1, then you would have some kind of rigidity. The main difficulty to push to full generality is that because it's bandwidth estimate, right? So this will give you the Lipschitz condition because the coordinate is smooth, but you only have Lipschitz. So the difficulty is that part. Yeah.
Is that part? Okay. Okay. Thank you. All right. One last chance. If people want to ask a question, or we'll thank our speaker again. Thanks again for the great talk. So.